Um, yes, security is an interesting subject. We're going to talk a little bit about how different operating systems do security. We're going to talk about a few challenges they all tackle in the same way. We're going to look at desktop OSs. We're going to look at mobile OSs. So let's just start. So yeah, we're going to look at it from an end user perspective. We're going to look at security, how it affects you as a user, not how a business or necessarily a server is going to be affected, but how you as a user is affected. So we're going to look at some protection mechanisms that are in all OSs, which I mentioned a little bit earlier. We're going to look at each OS by themselves, and we're going to look at some weaknesses. We're going to look at some strengths. We're going to compare them. It's hopefully going to be a little fun. So the biggest security risks from an end user are sadly not OS specific. We're still going to mention them. You have scamming and phishing, which we mostly just mentioned so we can show this hilarious little picture here from a failed scam, which is, to paraphrase it really quickly, one guy trying to scam a guy out of his knife, saying, no, it's not my knife, it's a friend's. Well, what's your brother's name? He changed his name to the guy's brother. Hey, it's me, your brother. Very infamous online. Only reason we show it, because it's funny. Browser vulnerabilities are probably the biggest flaw, the biggest risk from an end user perspective. Sadly not OS specific, so we're not going to talk that much about it. We're just going to mention it. Yeah. Let's move on to OSs themselves. Some of the security mechanisms they all share. The first one we're going to talk about is called protection rings. You have these different rings. Whenever you run a program, it runs in one of these rings. Now you'd think, oh, there's 4 rings. Most operating systems today, they're going to use all 4. No. You can basically ignore ring 1 and 2 because they just don't use them. Basically, what these mean is most of your applications like Skype, TeamSpeak, all that stuff runs in ring 3. They don't have access to kernel level functions. They can ask the kernel for I/O, memory access, stuff like that, but they don't have access to themselves. Anything risky is run in, not risky, anything that needs absolute security runs in ring 0. There's a tiny, so I say modern operating systems only use two rings. It's actually wrong, because if you run an OS in a virtualized environment, you actually use 3 rings. However, the last ring you use isn't shown in this picture. The last ring you use is something called ring -1, which is where your VMM, your virtual machine monitor, runs. But that's a special case, so it's not. It's a special case. We still mention it because it's there, but yeah. ASLR. All OSs today use something called address-space layout randomization. Now, what that does is the way your memory layout looks every time you run a process is going to be different. They're going to be randomized in, I think the example from Windows Vista was that your memory can look one of 256 different ways. Now, how that affects you is that if there's an exploit in a program and someone is trying to abuse a vulnerability to get access to your system, is because of ASLR, unless their attack is very, very sophisticated and defeats ASLR, which I'm not saying that doesn't exist, because that does exist. However, ASLR means their attack has a pretty high chance of failing, because where they're trying to jump in memory isn't where they're trying to jump a place where it might be, but it's most likely going to be the wrong place because of ASLR. ASLR was, we'll do questions later. ASLR was added in Linux in 2001. Windows didn't pick it up until Vista, and mobile operating systems picked it up around 2010. But it's a feature on every OS right now nowadays. Sorry, words got a little jumbled there. You can turn it off if you really, really want to. You shouldn't, but your system allows you to do that if you really, really decide to do it. We're going to jump over to operating system specific here. Linux is probably the safest. Well, I say Linux, but I'm taking Linux as a whole here. Probably the safest system you can run as an end user. That doesn't mean, oh, I'm running Linux, my system is always secure. That's not how it works. But it's a lot safer than if you were to run, let's not mention, but it is the safest. It has the potential to be the safest. You can harden it the most if you so desire. Linux is very decentralized, which benefits you as an end user. That means your specific flavor of Linux has to be vulnerable. And there's a million different flavors of Linux. Most people run one of the most 5 popular ones, of course, but so how is Linux secure? That's a complicated question, but just need to collect myself for a second. It's hard to put exactly into words. We could talk about a few things, namely open source. Linux is open source. Not everything is open source necessarily, depending on your distro. However, most distros are completely open source. You can look at the code for anything. You can just go online, look at the code for your specific flavor of Linux. Oh, that's how they do that. Now, what that means from a security perspective, you'd think, oh, that's bad. Other people can look at the code. They can find vulnerabilities. Yes, but other people can also look at the code. Oh, this is vulnerable. We can fix it. We can submit a fix. The fix will be out the next day. That's not going to happen on a closed source system, sadly, because, oh, you find an exploit on Windows. You can tell Windows about it. They might do something about it, but that might take them a week. It might take them 2 weeks. Who knows? I am talking a lot faster than I thought I was going to talk. So, what else can we talk about? Okay, yeah, package managers help you as a user from a security perspective. Basically, most software you install on Linux, you install through a package manager. That means you're not going to some shady website to download it. You're going through your distro's official repos, getting software. It has to be vetted to get in there. Depending on the distro, the vetting process is a little different, of course, but it is relatively safe most of the time. That doesn't mean exploits don't come in through the package managers, because they do, but it's very, very, very rare. Let's move on. OS X. Probably, sadly, the operating system I'm least qualified to talk about, but they share a lot of similarities with Linux. OS X is, as you all know, Apple's operating system, Apple's desktop and laptop operating system. It started as an offshoot of BSD. For those of you that don't know, BSD is it an offshoot of Linux? I think it's an offshoot of Linux. Not 100% sure. Don't quote me on it. A lot of things are done very similarly to Linux. It runs the Linux kernel for that. OS X has been called a walled garden, not as much as iOS, but is relatively walled off, which is good for you as an end user and bad for you. It's good for you because you're not going to run things that Apple don't want you to run. It's bad because you might want to run things Apple don't want you to run. So it's good and bad. From a security perspective, it's good. If you want to run the software you want to run, it's bad. So, Windows. The least secure of the 3, sadly. Also the most popular of the 3. Back before So what was this? Back in XP days, for those of you that still remember Windows XP, it was very, very, very insecure. If you would run any program you ran as your user, ran as if your user was an admin user, all your programs ran as admin. This was something I didn't mention, but because now all OSs have if anything needs to run as admin, it specifically asks you, hey, should I run as admin? Back in the XP days, it didn't do that. Anything, if you were logged into an admin account, everything ran as admin. This is really, really, really bad from a security perspective. This means basically every program you would run when you were logged into an admin account had the possibility of taking over your entire OS, because you could do that because you had admin access. Nowadays, Windows has UAC, which was added in Windows Vista, which means, oh, hey, it looks like this is trying to do some admin level stuff. Do you want to authorize that? Which you might want to do, because sometimes you want to have access to admin level functions. That isn't a problem nowadays. Both Linux and Mac has done this for decades. Usually the way it's done in Linux is basically your account isn't actually an admin account, but it can be elevated to an admin account when it needs to. So either you su into an admin or you use something called sudo, so you run the program as admin. Let me just restate that. Running everything as admin is a really, really, really bad idea. Sometimes, if people weren't malicious, it wouldn't be a bad thing. But the problem is people are actually malicious, so it ends up being a bad thing. Still talking way too fast. A little breather. Android and iOS. So there are more mobile operating systems, of course. However, nearly every single device runs either Android or iOS. They're relatively similar from a security standpoint. There are two major differences, namely Android, namely installing from third-party app stores, or just installing whatever you want, basically. On Android, if you want to install an app that isn't on the Google Play Store, you can do that. Whether you just go on your computer and use, I forgot what it's called, Android Studio, I think it's called, where you can just transfer it to your phone. Or you can install it through a third-party app store. You need to check a box. That's it. From a security standpoint, that's not very safe. That's not necessarily a bad thing. I mean, it is bad, but if you use it with a clear head, it's okay. For instance, when Pokemon Go was released, if you had Android, when it was released anywhere in the world, I think it was released in the US first. If you had Android, you could install it in Norway the day it came out. On iOS, you couldn't do that. So it's good when you just want an actual app. It's bad because a lot of things you find on third-party app stores aren't exactly apps you want on your computer, or sorry, your cell phone or your tablet, for that matter. On iOS, you can install things outside the Apple Store. However, you need to jump through a lot of hoops. Mainly, you need access. You need a developer's license, which costs a bit, and through that you can install it from your Mac. I think you need a Mac specifically. I'm not 100% sure. So we're not going to mention Windows Phone, because who has a Windows Phone? I don't know what their market share is. I would assume Windows Phone runs a lot like Windows. I'm not 100% sure on that. Yeah. I don't know. I don't remember if I mentioned this, but both Android and iOS also use ASLR. Most phones nowadays are essentially a very, very weak computer. Their use cases are very different, which is why we compare Android and iOS together versus Windows, Linux, and Mac OS X, which were compared against each other, because your use cases for a laptop or a desktop vary very much with what you want on your phone, or your tablet, for that matter. A lot of our use cases overlap, but most use cases are very, very different. I have a bonus that I want to show you guys. It's not a modern operating system. You could call it an operating system, but it's not exactly a modern operating system. So those of you who are familiar with UIO might know that we have a course where you write your own operating system. Now you might think, oh, my own operating system, that has to be a lot safer than something else. Well, not necessarily. We have an exploit for that too. So I'm just going to run this image in an emulator. Here we have an operating system. It doesn't look like much, because it's a very simplistic operating system. It runs a few threads. It has a shell. We can run programs in it. We're not going to talk that much about the OS itself, but there you see we have 5 different processes we can run. We'll load the first one. Okay, we have an airplane that flies across the screen. Oh yeah, bonus with the airplane, we can type fire to shoot, which if you're paying attention, it removes letters. Load 2, okay, something that counts. Process 3, that doesn't seem to do anything. Ah, typed it wrong. Process 4, which counts up between them. Now we get to the interesting one. And I almost wish I was running this on hardware and not in an emulator, because it looks amazing on hardware, but in an emulator it goes a lot quicker. So it gets a little flashy with lights. Either way, you just need to see it. Suddenly, everything else we knew about the OS is gone. We have some blinking lights and a guy smiling. If you give it also says pawn success up in the corner, if you see that. And suddenly, instead of running the OS we were running, now we're running Kim Il OS Reborn. It's a bit. See, this is where I mentioned it. This would look a lot greater on actual hardware instead of in an emulator. You see, it goes by really, really quickly. That's a byproduct of the fact that it's emulated versus run on hardware. Because he does funky animations with his face. It's great. I really wish I could talk exactly what happens in this exploit. Because I really wish I could talk about exactly what happens. This is relevant to modern operating systems. However, I'm sadly not allowed by the teachers of the course to explain why that happens. I went through all of my material way faster than I thought I would. So I think we move on to questions. Yeah, but we need microphone. Yeah. Yeah? Oh. There we go.
Hi.
Hi.
Can you hear me?
Yep, can hear you perfectly fine.
Is there any performance hit from the ASLR?
Is there very negligible? Negligible? That's a complicated word, but yes, there are very minor ones.
Okay.
Nothing extreme.
Okay. How does the program, or how do the applications actually know where everything's moved to, or does the operating system
The
handle
operating
that?
system keeps track of it.
Okay.
Keeps track of it.
Cool. Thank you.
On Android and iOS, you have to ask for permission
Yes.
to use anything.
Yes.
Is there a reason that this isn't done on desktop operating systems?
It's a relatively new idea, is one thing. I can't tell you exactly why. It is a very interesting concept, and I would love to see it in a modern operating system.
I do know that Chrome OS uses it.
Does Chrome OS use it? Yeah, but as your use cases expand, it gets very messy when you get a lot of programs. There are some performance loss with how at least Android does it, because in Android, every single app is its own user. It's a very messy way of dealing with it, but so on your Android phone, every single app you have installed has a user of its own. That is how they handle what they have access to. For if they have access to the camera, if they have access to disk, so on. It's not performance. It's not that much of a performance loss on a phone because you don't have that much installed. The more you have installed, the more of a performance loss it is. Though that being said, it is a very unique way of dealing with, okay, we don't want these things to have access to disk, or I only want these things to have access to disk, rather. I only want these things to have access to my camera, so on. It is a very good way of dealing with it. However, I don't think you're going to see it on most desktop OSs for several years. But I could be wrong. Any more questions?
I was wondering a bit more about the ASLR. Was it?
ASLR, address space layout randomization.
Yeah.
Yeah.
Why can't the programs read? I'm guessing there's a mapping between the.
There is a mapping.
Yeah. How is that mapping unrestricted?
So basically, the way it works is you have, you run a program, it will run in a certain place in memory. However, the differences between like the specific memory addresses inside the program are going to be mapped slightly differently every time you run. The OS keeps track of it, so when you say, oh, I want to have access to that specific part, that's fine. And so when the application itself uses it, it's fine. Because the way the application addresses the different memory locations, this works fine. However, when you're in exploit territory, you usually have like raw addresses themselves. And those raw addresses won't point exactly to what they expect them to point to. So they'll point, well, let's say they're trying to go to memory location 10,000 because they know, oh, there's supposed to be something at 10,000. However, it could be anywhere between maybe 5,000 and 20,000 because of ASLR. It's not that much of a gap, but it means they want to find something that's here, which is supposed to be here, but it could be in any of these locations, which makes it a lot harder for an exploit to actually damage your system.
Couldn't they just search?
Would you say?
Couldn't they just search the near area for the correct address?
Yeah, but
Is it too slow?
oh, I simplified it a little bit. It's not necessarily a linear area.
Right,
It's just
yeah.
random, somewhere
Right,
in
yeah,
memory.
so, yeah.
One thing I forgot to talk about is something called a stack canary, which I'm not 100% sure if that's OS specific or if it's programming languages. Basically, what they do is when you have, it will insert random values in the stack of every program that runs. Maybe it will say, oh, hey, X is 500. And then a little later, it's going to check, is X 500? And it's only going to be specific values that aren't in use in the program running. If it notices that X isn't 500, X, like the canary it placed has been overwritten, it will go, oh shit, something went wrong here, we're going to crash. It's somewhat related to ASLR, because they both help prevent the same kind of attacks. But even canaries aren't perfect. There's loads of attacks against everything. Any more questions?
In Linux, you
Yeah.
have to run programs in kernel mode
Yeah.
to get access to the memory directly, don't you?
Maybe?
I just wonder, maybe on other operating like Windows OS X that you SLR would be more important because it would be easier to get access to the memory directly because you didn't have to jump through more hoops.
Yeah, but you can access the memory directly without having kernel or administrative powers. Yeah, no matter
Yeah.
but yeah.
Yeah, but does no operating system give each application a specific part of memory
Yes.
and doesn't allow it to
Yes.
do something outside of that
Yes.
unless it's running in kernel mode?
Unless it's running in kernel mode, and then then it has different. But it's sometimes, but yeah. But it can be very important, even in Linux, when you have a program that has a SUID bit. A SUID bit basically means the program runs in kernel mode, despite the fact that it can be run from any user. These are very dangerous, because if there's an exploit, you suddenly don't need a privilege escalation exploit to get kernel access, because now you just have kernel access. But yes, like you mentioned, it's the same in all modern operating systems. Every process only has its own little piece of the memory pie. If they try to go outside of it, the program will crash. The system will notice, hey, you're doing something you're not allowed to do, stop it. But it's still, ASLR is still important because most exploits work by, whether it's buffer overflow or similar, they push a lot of malicious instructions to a specific point in memory, and then they jump to that point in memory. When you have ASLR, that point in memory isn't necessarily there. It can be here, it can be here. So if that explains it a little better. Any more questions?
From what I know about game hacks, wall hacks, that sort of thing,
Yeah.
they at least used to modify memory directly. It was how a lot of them were done, or at least read memory to find out a lot of data. Obviously, hacks still exist. How do they avoid or get around ASLR?
Well, first of all, if you want to run it, that wouldn't necessarily be a problem because you know you can turn off ASLR on your own if you really want to. Secondly, there are ways of referencing ports in memory with ASLR that won't necessarily violate. They just access it the way the program would access it, and that's how they reference memory directly. Any more questions? Should we just finish?